Hey folks, welcome back. It's time to add aerodynamics to our simulation. So what I'm going to do is I'm going to head over to Kerbin Wiki Aerodynamics, air density. Oop, that's not how you spell density, but I'm assuming I'm pretty sure there is let me zoom out. Yeah, here we go. This is what I want. So here is altitude, pressure, pressure atmosphere, and then density. And basically you can see at 70,000 meters EGL, the density is essentially zero. I mean, really at 50,000 at zero. There is probably an equation, like an exponent law, um, somewhere, but I've always just used this table just because it just seems kind of easy. So what I'm going to do is I'm going to create a new, whoa, that's not how you create a new file. I'm going to create a new file and I'm just going to drop this in here and I'm going to save this as Kerbin Aerodynamics dot, and not pi, but I'm just going to call it a text file. Okay, so it is a text file. Then what I'm going to do is here's where I set all the parameters. At the beginning of the script, you see how I test surface gravity? I'm going to import the aero model. Okay, and I'm curious, I want to make this a global. I kind of want to make this a class. I feel like this is going to be a little bit ridiculous if I do this, but I kind of want to do it just because I feel like it'll be kind of cool. And maybe you'll get excited about some object-oriented programming. So I'm going to create a aerodynamics class. So I forget exactly how to do this. I think there's a def init routine. You give it self parent equals none. And then in the init routine, this is where I'm going to read in the thing. So here, when I import the aero model, I'm actually going to do this up here on the planet. And so I'm gonna make a variable called name, and this is going to be Earth. And then down here, this is going to be name equals Kerbin. And the reason why I do that is because here's where I set all the parameters of the rocket. I'm also going to create a aerodynamics file. So I'm going to call it I'm going to say aero model equals aerodynamics. Okay, and so I'm going to create the aero model variable, which is an instance of the class aerodynamics, and I'm putting it up here so that it is a global. Okay. So in the init routine, I need to give it I'm going to give it the planet name, right? So that's the name. So it's going to be self. I'm going to get rid of this parent equals none, and I'm just going to give it name. And then I'm going to say if name equals Kerbin, then here I'm actually going to do self.name equals name. So that basically is I'm going to take the input name and save it into the class. So if the name is Kerbin, this means we need to import the aero model for interpolation. Okay? Else, I'm going to say elif name equals Earth. Then we just are going to use the Earth aero model. And I have this code somewhere. Let me just pull this up real quick because like I said, I've done this before. Let's see, Python. Sorry, let me delete all of this. Wow, forget it. You guys can see what else I'm working on. Aerodynamics, here it is. And then KSP2D. So I feel like I've done this before. Isn't there a beta term? Is there a beta term in here? There is not. So let me pause. Okay, here's the code I was looking for. So there's this term called beta, and it's a density constant for Earth. And I'll explain a little bit more in a second. But basically what you do is, I'm going to say, let's see. I'm going to make beta an input. Beta is an input. I'm not going to do that. I'm going to do it up here. Okay, and then self dot. Okay, so this beta term is an exponential term, and then this says density at sea level. Okay. All right, so those are the parameters that we need if we're going to do Earth, because then we're just going to use an exponent model. If we're using Kerbin, we need to import the air density data. So we're going to do load text of Kerbin Aerodynamics, and hopefully, let's see if that runs. Aerodynamics is not defined. Of course it's not, because it is defined here. I guess I need to, do I just need to put the, oh gosh, nope. Oh gosh, I've been using Sublime all day, and I'm pretty sure I am just destroying the, okay, so I want to open this, okay, and then I also want to open, oh shoot, you know what I forgot to do? I forgot to save this as a different file. Okay, so I'm going to have to do file save as and call this two-stage rocket with Aerodynamics. Okay, and then I'm going to have to open terminal and go to GitHub and Python git status, and it's going to say you edited the two-stage rocket, and I'm going to look at git diff of Aerodynamics rocket 7i series and two-stage rocket.py, and it's basically going to say I only changed this. Okay, so cool. And then these new files, it's not tracking those. So I'm going to git reset -- hard head, and then the two-stage rocket file should now be not changed. Okay, so now the original file is restored, and I can keep editing this. So what I wanted to do was I wanted to Control X this, and then Control V that in there, and then run F5 again. And then now it says wrong number of columns in load text. Okay, so the problem is this is a space, and these are tabs. So this needs to be a space, space, and then those look like spaces, I hope. If they're not the same, yeah, they're not. Okay, so what I'm gonna do is I'm gonna do a Control H, Control F, Control F. Okay, there's two things I can do. I can try to set the delimiter to a space and see if that works, and it's still gonna give me trouble. So then the other thing I can do is I can manually put a comma in between all of these. But I kind of want to just do the find replace function, edit. And I guess I don't know how to do this in Sublime or in Spider, so I'm going to do it in Sublime. So I'm going to go to Aerodynamics, Rocket Seminar Series, here, and I'm going to do Control H, replace the space with a, whoa, what's going on here? That's 69015. What is that? 69. Oh, weird. That's what's happening. Okay. So how did I not see that in Spider? Let me go back. Oh, interesting. Okay, so I just need to get rid of these. It's just the format of the file is not right, because there were those random spaces. So this is 101,325, I see. This is pressure. Okay. All right, let's see if that works. So if I run that, okay, that looked like it worked okay. So now let's print the data just to make sure that we're importing the data properly. Okay, cool, we are. So then we can do self dot. Now we got to look at the first column is altitude. So self dot altitude is data of all comma 0. And then let's go ahead and print self.altitude just to make sure that we got it right. And it looks like we're grabbing, 0 to 70,000. Okay, so I can comment this out. And then self.density, which is what we really care about, is 0, 1, 2, 3. So it's the third column. So it's going to be data all comma 3. And then just to make sure, let's print self.density and run that. And it looks like we got 1.225. And then what I'm going to do is I'm going to say self.rows is self.density of 0. And the reason why I did that is because self.density is defined here. And then just in case, I'm going to set beta equal to 0, even though we're not going to use it. Okay? All right, so now at some point we need to make a function within the class called getDensity. And the input is going to be self, so the class itself. This is just how object-oriented programming works in Python. And then you also have to give it the altitude, okay? So then if self.name is Kerbin, okay? And this is why I made this variable up here in their init routine, was so I could use it everywhere else. So this is where we interpolate, okay? And then there is an interp1d Python function. Okay, it's from SciPy. Wait, is it from SciPy? There's not like a numpy interpolate. Yeah, okay, I'd rather use that so I don't have to import a new module. So you give it x, which I guess is the x coordinates at which to evaluate the interpretive values. And then xp is the coordinates of the data points, and then fp is the coordinates, as the y coordinates. Okay, so what we're going to do is we're going to say row, and I don't need to do self because I'm just going to return this, is np.interp, right? And it's going to be the, let's see, I feel like my computer is lagging, so I'm just going to get rid of that. So it's x, so it's the value that I want to interpolate, so that's altitude. Altitude. Then the x coordinates, which is self.altitude. And then the y coordinates, which is self.density. Okay? Then elif self.name equals, not Kerbin, but Earth. Well, then you're going to use special equation. And what you're going to do is I think this, I'm trying to think, like if I divide by 1,000, is that like in kilometers? Like maybe we should go back to that ballistic reentry. This is row at sea level. Yeah, CHA. Yeah, so that's in meters, right? So beta is in units of meters, and I guess, it's because this is a weird unit. This beta is in units of inverse kilometers, so you need to divide by 1,000 to get inverse meters. Is that right? If I'm in 1/kilometers, right, and I want to convert that to 1/meters, yeah, that's 1/1,000, because 1,000 times 1 meter is a kilometer. Okay, yeah, that makes sense. So that means that this beta term is in units of meters. So if I want to use a special equation, rho is np.exp times, I think it's got to be negative, right? Negative beta times altitude. And then times, oh boy, what did I do? Times rho s. So if altitude is 0, you just get rho s. If altitude is really, really big, this number is going to get smaller and smaller until it rolls off to 0. Okay, and then we're just going to return rho. Okay, so what we can do is down here when we test the surface gravity, we can plot the air density as a function of altitude of AGL above ground level. And so I'm going to make a, I'm not going to call it altitude, I'm going to call it like, yeah, test altitude is going to be linspace 0 to, where do I want to go? I guess I'd like to go to 100,000. I'm just going to do 100 data points. I'd like to go to 100,000 kilometers. Sorry, 100 kilometers. And then I'm going to say test rho is, so this is where I should be able to use my class now, which is aero model. And so I should be able to do, oops, where is this? Here we go, aero model dot get density and give it the altitude, which is test altitude. And then I should be able to plt.figure, plt.plot, test altitude, test rho, sure, do it in blue. X label is altitude in meters, and then Y label is air density in kilogram per meter cubed. Throw in a grid, and I think that should be it, hopefully. So we should get an extra plot. Okay, so somewhere in here I did not do a plt.figure, plt.figure. So let's try again. And there we go. Okay, so that looks good. So there's the air density as a function of altitude, and it looks good to me. And it also means that like we've interpolated outside of that altitude, and so we're good. So this routine is working. It's giving us aerodynamics. So I'm going to leave that test script, that test plot down there, just so we have it. But now I need to add aerodynamics into here. Now the reason why I needed the air density is because the air density as a function of altitude is really, really important. So in this derivatives routine, I'm going to make a global and call this, I'm going to make my aero model a global. Okay. Oops. Aero model. I don't know why you're doing that. Okay, and then in here, I'm going to get rho is equal to aero model dot get density, and then the altitude. Well, what's the altitude? Well, the altitude is our planet. Sorry, it is r minus our planet. Well, what's our planet? Well, I'm going to make that a global as well, because our planet is defined up here, right? At 600,000 meters, okay? Then, it doesn't like this. Undefined rho s. Oh, I forgot about that because it's self dot. Thank you for pointing that out. That would have been a bug in the code. All right, are you done? Undefined beta. Oh, wow. I had multiple. Man, that's really cool error checking in there. All right, is there anything else in here that's giving me? Ooh. What's going on here? Undefined variable r. Okay, yeah, obviously. R is... Now here's something slick. I don't want to compute this twice. So the gravity model, I think, computes r. So I'm going to have it return the acceleration and r because it already computes it. And so this model is going to also return r. And then are you going to give me issue now? And then this just say it's not used, which is fine. Okay, so then we're going to compute what's called Q infinity, which is dynamic pressure. And that's 1/2 times rho times s times CD. No, yes. Well, actually, it's just 1/2 rho times s times v squared. That's what it is. Okay? So there's a couple things in here. First, what's rho is, I just defined it. What's s? Well, s is the cross-sectional area of your rocket. So here are the parameters of the rocket. So I'm going to assume that s is, well, what's the diameter of this rocket? Well, this is a Kerbin rocket. So I don't know. 20 feet across? trying to think, a Kerbin fits in the crew module, right? And I bet you maybe 5 of him, 5 times, that's like 15 feet. I'm just going to call it 15 feet divided by 3.28. So this is the but that's the diameter. So I'm going to call that the diameter, right? And then the cross-sectional area is NP times pi times d over 2.0 squared. Okay, so there's the cross-sectional area of the rocket. And then what's the drag coefficient? Well, that's hard to point out. I'm just going to put 0.4. 1.0 would be like a block. 0.5 I think is a sphere. And so I'm kind of thinking it's like a slender rod. And so I'm thinking like 0.4. Really, really fancy cars are like 0.2, right? They have very, very low drag coefficients. But we didn't put that in there because we just have the cross-section area. But I added the drag coefficient in there anyway because we're going to do Q infinity times CD, and then, and actually I'm not going to do V here. I'm going to do the absolute value of V. And then instead of putting the V squared in here, I'm going to put the X velocity in here and then the Z velocity. So basically the X velocity is going to multiply by that V to give you the V squared. And then I'm going to put a minus sign here to basically give me a this is going to be a force that opposes motion. So I still need V, which is the total velocity. So the total velocity, so altitude, this is altitude above the surface. This is air density, and then this is square root, and I think it's NP dot square root of vel Z squared plus vel X squared. And I think that's it. You didn't like it. Invalid syntax. Really? No, okay, it went away. Okay, so let's do this just for kicks, all right? I'm going to make the drag coefficient 0, and I should get the exact same orbit. No, I didn't. Because, oh, I'm sorry. So I didn't look at the syntax properly. This gravity model returns the x acceleration. Okay, so this needs to be a little, okay, so we're actually going to end up adding a line of code. So we're going to call the gravity model and get accel, comma r, and then we're going to take that accel. So the gravity model is outputting the accelerate, nope, that's the thrust model. The gravity model is outputting the acceleration and then the radius, or sorry, the distance from the center. And so we're going to call the gravity model to give us acceleration and then the distance from the center. And then we're going to use acceleration to multiply by mass to get the gravity force. And then we're going to use the radius, or sorry, the distance from the center to the satellite, subtract it from our planet to get the altitude. Okay, so I just made the drag coefficient 0, so we should get the exact same orbit. And we do. Now my question is, what is altitude? Altitude dips to 61,000 right here, right? Which is not, I guess, not very low as I thought. But yeah, I mean, that's basic. Well, I mean, it's not non-zero. So if I make my drag coefficient 0.4, oh no, the whole simulation blew up. Okay, so, ooh. Is it possible that we didn't even get off the surface of the planet because the drag is so bad? It's possible. Let's print arrow F. Okay. And then let's print thrust F. And then let's also print. We're doing some on-the-fly debugging here to see what's going on. We're going to print gravity F. Okay, and then I also want to print the total forces. Okay, and then is there like a pause function? Like I want to like, there's a pause in MATLAB. There's got to be a pause in Python. Sublime? No. Google. pause in Python. Yeah, pause top wait. That's what I want to do. I guess we could do a time.sleep. That seems like a really, really bad way to do it, but I mean, sure. So let's do a time.sleep of like 1.0 seconds. So we can kind of read it as it's going. And then I guess I'm going to need to import time here. All right, so let's run that. Okay, so that's obviously too fast. Let's hit Control C. Okay, so what are we printing? So we're reading, and then let's do here print like, this, so we can kind of get like a differentiation between what we're doing. So let's pause for 5 seconds. So the first one is gravity, then aero, then thrust. So the first one is gravity, which is huge, then aero, which is 0, thrust, and then total. So total is positive at 11,000. And then aero is slowly creeping up. That's what it seems like. Okay, but it doesn't look like it's something crazy. So let's comment out all of these. Okay, and let's just make sure that this is making sense, right? So 1/2 rho v squared s times cd, and instead of doing v squared, we're doing the absolute value of v times vel x and vel z, and that's giving us, yeah, and then we still divide by mass. I mean, we're still doing force divided by mass there. So I think we're good. I mean, it might just be that we have too much drag. So I mean, maybe I overestimated the diameter. I said it was 15 feet. That doesn't seem that big. I mean, let's assume it's 10 feet, and let's assume our drag coefficient's like 0.2. Then what happens? Well, what happens is that you still have a print statement in there. So you still need to Control C it. It looks like you're still printing the total force and that dash sign, and you still have that time.sleep in there. So it still ran the warning. Yeah, even with like a little bit of drag, it can't get off the surface, which is kind of wild. Okay, well, tell you what did I, in my KSP2D, what did I say was my drag? Pi, why do I have pi? Pi rho SCD, absolute value of vel x times VLX, that's right. And then, but I divide by mass, that seems odd because I need a force. Where do I add in aero x? Here we go. I had an aero x here. Okay, that's why, because I already divided by mass. But what did I make S and CD? Where are those parameters? Are they down here? Yeah, it looks like it. Whoa, I made S 0.01. I made CD 0.1. Okay. Oof. That seems kind of wonky. And then what is S in this sim? 7.3, and I made it 0.01. Whoa. It's also possible that I'm using the wrong dynamic pressure, because I noticed that there's like a np.pi. I'm pretty sure for rockets it's np.pi over 8.0 rather than 1/2 rho v squared. And then it's still times rho, and then S, it's not S anymore. I think it's d squared. So if I do that, I don't need S anymore. What did that do? It still blew up. I wonder if it's worse. Yeah, it's pretty much worse. And it's actually kind of nuts because it like goes inside and then shoots out again, which doesn't make sense. Like this is like an invalid simulation. It's like it like ricocheted across the planet and then got out of the aerodynamics. Let's make this 0.01 like it was before and and see what happens. Okay, and then let's make it 0.1 now. Okay, let's make it 0.5. Like, I think, let's make it 1.0. Okay, 1.0 made it blow up, so 0.8. I want to see a simulation where it gets to orbit. Okay, now we're talking. So we are in orbit, but we are clearly, our orbit is clearly decaying. If I make it like 0.9, no, that's too much. So 0.85. It seems very, very sensitive. But yeah, there you go. I mean, there it's spiraling in. It's losing energy. So where's my period? 6,000. So if I simulate for 12,000 seconds, yeah, that still blew up. Can I got an idea. The simulation is having trouble because I said here if R is less than 0. Let's just go ahead and do our planet. Maybe it won't blow up. There we go. Okay, yeah. So as soon as we hit the planet, we crashed and the simulation didn't blow up. So see, now we can actually see the orbit decay as it comes in. Now the cool thing is, do we still have mass to burn? Like, do we still have a mass budget? Where's our mass budget? Here. We still have mass, right? So if we burn that second stage longer, right, like 20 seconds, can we get out of that aerodynamic realm? Yeah, that's cool. So if we burn a little bit longer, we get far enough away from the atmosphere that our orbit doesn't decay. But if we only burn for 17.5 seconds, our orbit isn't big enough, and right here we lose energy. Right here we lose energy and we get drag, and that slowly decays our orbit until, like, you can see what's happening. Like, right here is basically our perigee, and right here is our apogee. And so when we come in, our apogee basically comes in until finally you get into where your orbit collapses and you lose energy and crash into the surface of the planet. This is a good thing to do when you're playing Kerbin, if you have like a lot of time, because this will save your heat shield. So if you don't have a heat shield, this is the best thing to do, is to sort of like decay your orbit. So this is pretty cool. I think my video is long enough. I have no idea how long it is, but it feels really long. So I'm going to go ahead and end the video here. I mean, this basically has everything we need, I think. So if you want me to add anything else in, post in the comments. But I think as far as my class is concerned for spacecraft design, this is everything you need to simulate a two-stage rocket, at least in 2 dimensions. I guess I could convert this to 3D, but I'm not sure I want to do that. But anyway, my code is up on GitHub, and I hope you enjoy watching this video. And I'll see you in the next one.